Yeah, so good afternoon, everyone, whatever time it is. So, we are going to start this structural detailing of what we've been doing since all these days. And yes, so this is the whole detail of our structural design, the design we've been doing for the past 1 month plus now. So, this is basic a basic um, look of how structural detail is. So this long stuff that you can see here that looks like beam but not beam, that's the slab, and that is the section, cross section of the slab from the center, from somewhere in the center. So now these are the arrangement of the bars, and our main bar is the one that is always at the bottom. Now these are the preambles we given and then solved for, which are this is the span, the basic span of the slab, which is 9 meter, and the main bar being y16 at 100 mm. So that's how it is there. So now this is beam A and beam B, those are the supports, and then our main bar is the one under, so that's the y16 at 100. Then the distribution bar is the one you can see at the top has dots. So that's that. So zooming in. So the basic span, our basic span of the slab is 9 meter, which is effective from the center of the two supporting beams, beam A and beam B. So you start counting from the center of the beams. So that's that. Then our distribution, our main bar is y16 at 100 mm. Then our distribution bar is y16 at 300 mm. So that's according to the area of steel we designed for in our structural design. But this is the detailing of our structure. So now we are going to be taking, as I mentioned earlier, the main bar is the one at the bottom, which is this, and then the distribution bars are the dots that you can see as it is labeled. So that's so now so you can see how I labeled it, y16 at 100, and that, of course, the other one, which is the distribution bar, is y16 at 300, because it's only distributing the weights all over the main bar for it to be supported by the effective span. So now let's go to the curtailment topic. So our curtailment for slabs, yes, for simply supported slab, we curtail, meaning that we cut because we don't need some area of steel at some certain places, at some strategic places on our slab or beam. So the most effective side that we need our curtailment is at the center of every slab or beam. We have the maximum bending moment, which are always positive. So now from the support to about 0.2 length of the slab or the beam, those are the those parts are not very effective, speaking about bending moment. So that is why we are using lesser area of steel. That's what I just drew here. So this, from this place to this place, from this section, we have as you can see 1.8 meter, which is literally 0.2 of the span, which is 9. So you just multiply 0.2 by 9, you get 1.8. So now the area of steel we are going to be using there will literally be half of what we have at the center. Remember that the center one, like the center area or the center beam reinforcement arrangement, takes the whole of the provided reinforcement or the designed reinforcement. So but this part, we are only going to be taking half of it, because we can't extend the whole area of steel across the slab, because we really don't need them at the supports, because there is literally no zero to no bending to no moment or bending moment at the supports. They are mostly negative, meaning that you need those reinforcements at the top. But so now, since you've done that, remember this is a simply supported slab, meaning it is only resting on the beam, on beam A. So that is why we in fact don't need those areas of steel. They are not required. So we are just taking half of it. So you can see, as you can see here. Hey, so in this one, in the top one, our main bar is at the top, while our distribution bars are at the bottom. Remember, but for the bottom, or for the reinforcement at the bottom, our main bars is always at the bottom, then our distribution bar is at the top. While for the top reinforcements, the main bar is the top and the distribution is the bottom. I remember we are using half of what we calculated for, meaning that if you calculate for a y16 at 100, you are going to use y16 at 200. You've literally reduced the area like that by reducing the number of bars and increasing the spacing. I hope you understand. So now we are going to take for this overhang side. So our overhang length, I've forgotten the length actually. But then you can just basically use the same idea that we use here. And remember to refer to your textbook to our limit state design of reinforced concrete. It's really helpful. Go to the chapter of curtailment and you would really learn about how things work. So for cantilevers, we have our bending moment, which is always negative. So that means our reinforcement will be at the top. That is why we have it at the top here. And our main reinforcement is at the top, while the distribution reinforcement is at the top bottom, which are the dots that you can see here. So now we are going to take the whole of our area, our complete area, at the center, like at the center span, then half of it also, just as we did there on the other parts. So now our length for the overhang is so our overhang length is actually 2.7 meter. Then half of 2.7, that's where you are going to stop the complete area. So we are going to start using half of the area, meaning that you are going to reduce the area by increasing the spacing of the bars. So that's what we have there. So this is our main bar. That's y16 at 250, I guess. And so something else to note here, you can't use spacing that is more than, you shouldn't. It is not ideal to use spacing that is above 300. Don't use it. Never use it, especially on slabs. They are not practical. Even if you design for slab to have let's say y16 at 400, don't use 400, take 300, because that's the ideal. It shouldn't exceed 300 mm. So you can, as you can see, the curtailment here, the curtailment here from the center of the support to at least 1%, which is 0.1%, or 0.1 times the length, the basic length. Our basic length here, remember, it is 9 meters, so 0.1 of 9 meters is 0.9. Hope you got it. That's where our main reinforcement lies, meaning our complete area of reinforcement lies. Then anything you want to extend after that, you are going to use half of the reinforcement, meaning you are going to increase the spacing. But remember, again, the spacing shouldn't exceed 300 mm. So that's also that. So that's why I use y16 at 300 mm here. So according to the British Standard Code, there's giving you as part is British Standard Code. I actually don't know of other codes, but according to the British Standard, we can't use anything that exceeds 300 mm. So since that part is cantilever now, so now let's speak about this one. So this part is cantilever. We are just going to take literally half of it and extend your complete area of steel. Then anything further than that, you are using half of the steel provided, meaning again you are going to increase the size, or sorry, the spacing. And also note the spacing should not exceed 300 mm. If by design you have spacing more than 300 mm, just take 300 mm. That's the minimum requirement. So that's for slab. I hope you understand. Since I didn't label it here, I'm actually recording the audio. So I actually forgot to put the length. So this is a plan section, yes, plan section of the slab, but not to scale, as you can see. But basically this is how it would look. So I don't think I have much to explain again on this plan, since we explained it in this section already. This is not to scale. So from our knowledge in, I think was it structural drawing? Yes, structural drawing in internal level second semester. We did things like this, how to arrange bars. So this is the application of it. You are just going to basically put your knowledge into practice here. So this is the beam A. Remember from our section at the top. So the span from the center of of that beam A. So the other span is, remember, 2.7. So this span is 9 meters, 9.0 meters, and this is 2.7 meters. (9 meters), as you can see. So the main steel it still spans at the center. That is what you see at the center here. Can you notice you have two long or longitudinal bars? One is long enough, like that it extends throughout the span from the center, from just after the center of support A to just to the center of support B, which is the beam B. So this one that I pointed here is what we are using the complete area for. That's which is Y16 at 100. But then the long one is Y16 at 250. Yes. So that's basically what it is. So remember that curtailment is 0.2 L, which is 9. That's what I explained earlier. Also 1.8 meter. So that's what is 1.8 meter. So this beam is this bar is what continues, that spans throughout. Yeah, the one I said is extended to the supports. We are reducing the area by increasing the space between the bars. So just past the center, that is where it's going to extend to almost the center of the other support. So that's basically it for that. That's it for the longitudinal section of our slab. meaning from plan. So that's why it's seen at 300, because of course again we don't want our bar spacing to exceed the maximum allowable, which is 300 mm according to the British Standard Code as per the BS 8110. So what was explained earlier also, that we have a bar our cantilever, meaning overhanging span slab, which is 2.7 meter. So we are going to take half of the area, meaning that our complete area, we are going to curtail it, we are going to stop it at the center of the cantilever slab, then extend half of it by increasing the spacing. But remember, that spacing should not exceed 300 mm. So by reducing the size, the area of bar, we are increasing the space. So I think I made mistake here in the labeling. It actually should be you would extend minimum, which is half of the area, to 0.3 the span of the or the length of the span. But for the cantilever, as I said earlier, it is half of it. We are going to extend the complete area to half of the span, and extend the remaining one. So for our beam, our beam is spanning 6 meters, and the depth of the beam is 750. Because the total depth of beam, standard beam, as per the BS code, shouldn't exceed 750. That is why I capped it at 750. So I don't know, for some people that might have used 750, you can still do it like that, because it is not practical. We are just doing some theoretical work here. So from the center of the support to the center of the other supports of our support, that is where that 6 meter span lies, or that is where it spans through, from the center of the support to the center of the other supports. So the next thing is our depth. Our depth from here to this place, yes, from here to this, is actually 750 mm. So that's 750 mm. So the same curtailment idea goes with this also. But let's still, so our bottom bar, which is our main bar in the beam. So according to the BS code, you shouldn't have odd arrangement of bars. You should always make them even. That on every layer you should have at least 2 bars on it. So meaning if you have 9 bars, you would either do it 3-3-3 on each layer. Yeah, 3-3-3 on each layer, because you can't do it as 4 on 2 layers and 1 on the. Rather, you rather increase the bars to 10 rather than using 9. But then if you want to do it ideally, you would use 3-3 bars in each layer. But since here we have 12 bars already, So our 12 bars, we are going to arrange them in 3 layers, 4 on each layer. So dividing 12 by 6 by 2, I mean, we have 6 bars, but we can't use 6 bars since we have already we can actually use 6 bars, and that I did 4 on each layers. Yes, 4 on the first layer and then 2 on the other layer. That's 6. So that's complete. So this for this beam, this beam is quite different from slab. So our beam, the curtailment of our beam starts literally from 0.08 L. L is your span your beam span. So our 0.08 L here is 0.48 of 0.08 of 6 meter is 0.48, and that what we just did there. And remember, you are going to cut sections. You are going to cut one from the center to show to show your reader the full area of the steel at the center. Then one adjust the adjust very close to the support. So the bottom bars are actually complete as 12y25. So that's how that is. And then there's a top bar. There are 2 top bars, which is just 2y25, because you can't even have 1y25 in the first place. So you have to provide at least 2 bars at the top. So for some people who don't have the required or are not required to provide bars at the top, according to the code of practice, you have to provide at least two bars at the top. That's what they call construction bars professionally, but on field they call it anchor bars. So you have to provide anchor bars to at least for your stirrups to get held. So you are going to provide at least, and so those 2 minimum bars you are providing shouldn't be less than y12. I mean the size of the diameter, the diameter of this of the bars shouldn't be less than 12. So when you don't have any compression bar, just provide 12 just to meet the requirements. Yeah, so that is what down is. So as I said earlier, you would cut the section just by the supports, and you cut another section at the center to show your full span, your full span, or your full area, I mean. So you have 6 bars, the one at the supports. So now you would be advised to actually go back to your textbook and read on curtailments. That would give you a lot more insights on how curtailment is done, or even understand it better than me. So please subscribe to my channel. I'll be uploading more of structural works, or might probably start uploading software tutorials, like how to use some basic structural programs. So that's that for this. So the next work we are going to do after this is to prepare a bar bending schedule. So I don't know if you would like me to prepare a bar bending schedule. I want to get this video to about let me not put a cap on this video, or let me not cap it on this video. Let me have at least about 120 subscribers. I would make a video on bar bending scheduling. So thanks.